Hi students, welcome to my lectures on designing of non-ideal reactors. In the last class we have discussed about the segregated model, and today we have discussed about the maximum mixedness model. The basic difference is segregated model and mixedness model is as follows. And this is a non-ideal reactor in which you inject some amount of tracer will tell you the information about the time. Okay, so the thing is, in the segregated model we have discussed that there is a different age molecules in the reactor which we can able to find out through the tracer curve experiments, where between time 0 and t1 I have age molecules is 1, t1 to t2 age molecules is 2, t2 to 3t age molecules is 3, t3 to t4 age molecules is 4. That means the conversion comes from the all the different age molecules in the reactor. Through the tracer curve we have found out that what age molecules contributed to the conversions, because different ages different kind of conversion. In the segregated model it is assumed that the age 1 molecules will not interact with age 2 will not interact with age 3 and so on. Everything in the different age molecules they won't share the informations, whereas in the maximum mixedness model it is assumed that, example, the age molecules spend the time between 0 and t1. Okay, during this particular time it mixes with the other molecules. Okay, before it is exiting the reactor it mixes up with the other molecules. Similarly, age 2 molecules which are spending the time in the reactor between t1 and t2, between this time it will mix up with the other molecules and then it exit the reactor. So that means before the molecules exiting the reactor in this specified time, it say hi, hello to everyone and then it exits the reactor. That means that the information exchange takes place and mixing takes place with the different age molecules. This is what the basic assumption that comes through the maximum mixedness model. Okay, this is the difference between the segregated and maximum mixedness model. So E of t curve will be the same because the time spent by the molecules are the same when we compare the segregated model and maximum mixedness model. For example, the age 1 molecule will spend the time between 0 and t1, age 2 is t1 to t2, age 3 is t2 to 3t, age 4 is t3 to t4. In segregated model also the age spent molecules will be the same, but between this particular age it will interact with the other molecules before it exits the reactor. So that is what the maximum mixedness model talks about. So that is what has been explained in the words, I hope. Now let us see how people predict the conversion in this particular scenario. Okay, so this is what the basic the schematics people used. Our objective is to predict the conversion in this non-ideal reactor, using maximum mixedness model. People have assumed this particular scenario happening in the reactor. For example, a certain volumetric flow rate of feed is entering into the reactor, that is has been divided into number of segments. That means inside this particular reactor people have assumed this picture. What happens if you divide the volumetric flow rate into different sections in this particular kind of schematic? Some molecules enter at this point, some molecules enter at this point, some molecules enter at this point, some molecules enter at this point. The molecules which enter at the this particular position is going to spend a larger amount of time in the reactor before it exits. That means age 4 molecules in this particular reactor which spent more amount of time in the particular reactor. During the travel of age 4 molecules mix with 3, 3 and 4 mix with 2, 2, 3 and 4 mix with age 1 molecules. There are some molecules, example age 4 molecules, the one that enters here. Okay, these are called age 4 molecules. Then age 4 will become age because here the age 3 molecules. Age 3 molecules, okay, mixes up with the new, this particular age is going to mix up with 2 and 1. Age 2 molecules is mixed up with 1. That means different age molecules mix in this particular, that means all the mixing concept which is assumed in this particular reactor can be narrated using this particular description. Okay, so entire things exit here. If you follow the elements of chemical reaction engineering Fogler, so I have followed this particular book to explain the particular scenario. Here it is given time t equal to 0, here it is given time t equal to infinite. Okay, what is time t equal to 0? The molecule which enters the reactor exit at very early. So that is why t equal to 0, lambda is equal to age expectancy. So both are same. Some people use the lambda, some people use the t. Both are examples. Life expectancy. Life expectancy of the molecule which enters at this particular stage will exit early. Okay, that means life expectancy is close to 0. The molecules which enter at this position has certain life expectancy. So this two molecules are higher expectancy than one. H3 molecules which are going to spend larger amount of time in the particular reactor. So life expectancy of 3 is higher, and life expectancy of 4. That means these particular molecules spend very largest amount of time in the reactor. So this is how the mixing scenario is assumed. Volumetric flow rate divided into number of sections. At every section, this volumetric flow rate is divided. So new molecules enters at different positions. These new molecules mixes with the older age molecules, finally to give the conversion from this particular reactor. That means every possible mixing can be assumed in this particular scenario. So let us move forward in deriving the things. So lambda equal to 0, that means life expectancy is lower, and lambda equal to infinite, the life expectancy is here. So this particular scenario is assumed in the non-ideal reactor, and this is lambda equal to 0. You can see this particular curve here, lambda equal to 0, that means time t equal to 0, time t equal to infinite. So E of t curve. Okay, this is called E of t curve. So this is 0 and this is lambda. That means these particular molecules which enter here has a lower time in the reactor. This set of molecules which enter here has the highest amount of time because it has to travel through all the reactor before it exits. So lambda equal to 0 here, lambda equal to infinite here. Let us take a small section in this particular schematic which is assumed in this particular maximum mixedness model, which is happening in the any non-ideal reactor. Non-ideal reactor could be CSTR, PFR, packed, any reactor can fit in but this particular scenario. Okay, take a small section which has a differential volume delta V, and the life expectancy here is lambda. Life expectancy here is more than lambda, which is lambda plus delta lambda. Here lambda equal to 0, here lambda equal to infinite. Okay, there is no molecule that enters here. This section is closed. Okay, the molecule enters from the top. Okay, in this schematic. So the volumetric flow rate is divided into number of sections. Okay, the molecule can enter here or molecule can enter here. The molecule which enter here has a higher expectancy, and molecule which enter here has a lower expectancy. So we have to do some certain mole balance. So mole balance of the reactor can be volume at section here, the moles of A. There are two things that are entering in this differential element. One is from the left hand side from this particular arrow, second is from the top. So the one which is entering from the left hand side is nu into Ca at lambda plus delta lambda. The moles per second, that is molar flow rate of entering from this particular is defined as nu into Ca at lambda plus delta lambda. And one more thing that is entering here, which is the new molecules which is having this particular, because you can directly compare the residence time. So these are new molecules. These are molecules which having certain life expectancy here entering at this particular stage. You can relate the three curves. Okay, these molecules will enter this particular stage. So the molar flow rate is defined as nu 0 into E of lambda into delta of lambda into Ca0. Ca0 is the initial concentration of reactant which is entering at this particular stage. The exit is nu into Ca at lambda. So two are entering and one is leaving. The one which is entering on the left hand is the higher age molecules, which is mixing up with the new age molecules. That means 0 age molecules are entering here. Then the mixing scenario happening in this particular schematic. So the things were defined in this way. So based on this, we have to do the mole balance. How to do the mole as? You need to have certain steps, intermediate steps are there. I will give the intermediate steps as well, so that it is easy for you to contain. What is nu zero? Initial volumetric flow rate. The initial volumetric flow rate is nu zero. What is E of lambda into delta of lambda? That is area under the particular E curve. That means the fraction of molecules the entering at this particular stage. Okay, delta lambda is the life expectancy between lambda and delta lambda. What is nu zero and to E lambda into delta lambda, representing the fraction of volumetric flow rate. So this E lambda into delta lambda is the fraction of molecules. Fraction multiplied by nu zero is nothing but fraction of molecules entering from the top, which is total volumetric flow rate multiplied by fraction. Okay, this is set of molecules entering from the top. Okay, which is having the life expectancy of lambda and lambda plus delta lambda. Okay, what is nu zero? Unit of nu zero is liter per minute. E of lambda into delta lambda has the unit of fraction of molecules. So if you multiply nu zero, E of lambda into delta lambda into Ca0, which will give the molar flow rate of A entering at this particular element. So nu zero has a liter per minute, E of lambda to delta lambda has a fraction, Ca0 is a mole per liter. So if you combined these particular terms, that molar flow rate of particular stream entering at this particular stage is in mole per minute. Okay, so you have to remember few steps so that it will easy for you to understand. So let us do even before applying mole balance, let us do some volumetric flow balance. Okay, volumetric flow rate at this particular lambda plus delta lambda is nu at lambda plus delta lambda. Volumetric flow rate exiting at this differential element is nu of lambda. Volumetric flow rate entering from the top is total volumetric flow rate into fraction of molecules having the life of delta lambda. So if you do the mole balance, 2 ins and 1 out. 2 in is plus, 1 out is minus. So total n equal to out. Okay. If you apply the limit delta lambda tends to 0, then make it as a differential form. D of nu lambda by d lambda is equal to minus nu 0 into E of lambda. Now you have to integrate. At what integration? On the one end the life expectancy is infinite, on the other end the life expectancy is 0. So instead of infinite, you can limit yourself up to certain lambda, because there is no infinite time in the reactor. So one limit later on you can able to do it. One is infinite, that means one is on the left hand side, infinite, that means which entering the reactor at a very initial stage. That means here, I mean, you have to integrate on the left hand side is lambda to up to certain lambda. Okay, left hand side to right hand side. Therefore, if you lambda to infinite and this expression will become minus nu 0 into 1 minus of f of lambda. Okay, what is the volumetric flow rate from infinite to lambda? It is nothing but lambda. That means at this point, if you integrate, the volumetric flow rate up to nu lambda is nothing but nu lambda minus infinite to lambda, combining of all the flow rates. How I got 1 minus f of lambda? Here is this shortcut, I mean shortcut in the sense, integral lambda to infinite E of lambda into d lambda will have become 1 minus f of lambda. How it become f of lambda? I know the definition, f of lambda equal to integral 0 to infinite E of lambda into d lambda. Okay, this is the basic definition, that cumulative distribution and the residence time distribution. Therefore, I know area under the curve is 0 to infinite E of lambda into d lambda equal to 1. Therefore, lambda to infinite, if you divide this 0 to infinite into two sections, one is 0 to lambda and lambda to infinite. From this, lambda to infinite E of lambda is d lambda is nothing but 1 minus 0 to lambda E of lambda into d lambda. That is nothing but f of lambda, 1 minus f of lambda. Therefore, you can replace this lambda to infinite E of lambda into d lambda with 1 minus f of lambda. Okay? Yes. Then this is how we got this particular expression. Then what is the volume of the fluid in the reactor with life expectancy between lambda and delta lambda? That is this particular volume, which having a life expectancy between lambda and lambda plus delta lambda, is nothing but volumetric flow rate into time. So the volumetric flow rate is V lambda into life expectancy is delta lambda. So volume is nothing but the volume, volumetric flow rate has the units of liter per minute, life expectancy has the unit of time. So you both cancels out, you get delta V, that is volume of the element in this differential section is nothing but V lambda, nu lambda into delta lambda. then what happens to the rate of reaction? The rate of reaction in this particular, because simultaneously flow is coming and reaction is also happening. Then how to count for the reaction? Rate of reaction in the volume is Ra into delta V. Okay, Ra equal to Ra into what is delta V? Nu lambda into delta lambda. So if you substitute, you get Ra into what is V lambda? You can substitute this particular expression, Ra into nu 0 into 1 minus f of lambda into delta of lambda. With these particular set of equations, now we do the molar flow rate balance. You get the expressions. Okay, so now let us do the actual mole balance. Okay, in this reactor, let us divide in this differential element which is having the life expectancy of V lambda and lambda plus delta V lambda. And differential section has the differential volume of delta V, which is called delta V, which is a differential volume. So inlet concentration and inlet volumetric flow rate, Ca at lambda plus delta lambda plus nu at lambda plus delta lambda is the inlet. So exit nu lambda at Ca lambda. What is the inlet from the top side? Nu 0 into E of lambda into delta of lambda into Ca 0. Let us do the mole balance. Okay, this mole balance, okay, if you do in minus out minus consumption plus generation equal to accumulation. Now we are assuming the steady state. So the accumulation term is 0. The inlet, there are 2 inlets, 1 exit. So 2 inlet and 1 exit. Okay. Next thing is consumption. Reaction is getting, the molecules of A is getting consumed. So minus of rate of reaction into delta V. Rate of reaction is minus Ra into delta is in the differential volume element. So this is the mole balance. And if you substitute all the previous expressions in this particular equation, and then if you do some sort of mathematical integration principles, finally you are going to get an equation which is equation, that means equation in the sense how my concentration is varying along this particular length. At here the molecules which is entering here, the conversion, example the conversion, because molecule have just entered here which need to travel through the long amount of time. Here the concentration, the conversion is 0. As the molecules travel along the reactor, the conversion rises. That means at one end the conversion is 0, at the other end the conversion is maximum. That means at one end the concentration is the initial concentration here, at the other end the concentration is the final concentrations. Therefore, the final concentration, that means on the second end, the final concentration in this non-ideal reactor is represented in terms of this differential equation. If you can able to solve this differential equation, you can able to predict the final conversion. If you know the final final concentration, if you know the final concentration, you can able to find out the final conversions. Okay. Earlier this particular equation in terms of concentration, let us convert in terms of conversion also. You can able to simply convert this equation in terms of conversion using this principle, that conversion of A is nothing but initial concentration minus final concentration by initial concentration. If you apply this particular equation, substitute in kind of this particular differential equation, finally you get this is in terms of concentration and this is in terms of conversion. So finally dx by d lambda is Ra by Ca0 plus E of lambda into 1 minus f of lambda into x. Okay, what this means, you can see here, that means how my conversion is changing with respect to the length of the reactor. Here the conversion is 0 at one end, here the conversion is maximum. So how my conversion is changing along the time, lambda equal to 0 is lambda equal to infinite. Okay, this is what the equation is representing. Now let us solve one simple example. If a non-ideal reactor is following the maximum mixedness model, and what is the conversion we can expect from the non-ideal reactor? There is a small example, we can able to deal with it. Okay, find a conversion for a non-ideal reactor using maximum mixedness model. Okay, there is a reactor which is it could be CSTR or PFR or packed bed reactor. Because if it is behaving non-ideally, then my assumption is assume the maximum mixedness happening in this particular non-ideal reactor. If that is so, then how to predict the conversions? Okay, so given the non-ideal reactor volume, rate constant, which is first order reaction, and tau, which is a space time, and initial concentration, initial volumetric flow rate, and the tracer curve data is also given. Because from the tracer curve data we get E of t information, time information, F of t information. So the tracer curve data is important. So to solve this particular equation, we need to take the help of the Euler's method. This is a differential equation. Let us Euler's method. Okay, and Euler's method says that conversion at I minus 1 is nothing but conversion at ith point minus delta t into f of xi. That means you have to integrate at conversion from x equal to 0 to x equal to something. That means here the conversion is 0, here the conversion is maximum. So how to predict the conversion? You need to do it that f of xi, that means you have to simply you need to have the basic idea of numerical methods, how to solve this particular equation using Euler's method. So time t equal to, that means you have to integrate backwards. Okay, time t equal to question. You have to time t equal to 5, you have to come up to time t equal to 0. That means here the conversion is close to 0, here the conversion is to 1. That means you have to start from conversion equal to close to 0 conversion to the maximum conversion. That means you have to integrate from time t equal to 5, come back time t equal to 4, 3, 2, 1, because the data is given 5, 4, 3, 2, 1, 0. So you have to start with time t equal to 5 to time t equal to 0. So time t equal to 4, that means the conversion at time t equal to 4 is nothing but conversion at time t equal to 5 minus delta t into f of conversion at time t equal to 5. That means 4, you have to find out the conversion at t equal to 4. Like that you have to do this till you reach to the time t equal to 0. That means you have to do the Euler's method. Okay. At time t equal to 4 is nothing but time t equal to 5 minus delta t into function of time t equal to 5. Then how to get the information of function? Thus function is given. Okay, that function is minus the RA by CA 0 plus E of lambda by 1 minus F of lambda into X. This is the function. Okay, the RA equal to minus KCA, we already know this information. Okay, it is given as this is RA equal to minus RA equal to KCA. That means this particular information is already provided. So if you put it in this particular term, RA equal to you can see RA equal to minus KCA, CA equal to CA naught into 1 minus X. So this CA naught cancels out, and finally you're going to get this particular kind of expressions. So f of x is this one. Okay, you need to find the conversion at different times till you reach to the value t equal to 0. So to find these values, you need to find what is the f of x. F of x need information about k, E of t and f of t. Let us find out E of t and f of t values at different times, so that you can able to put it in this particular respective expressions to find out what is the final conversion that you are expecting from the reactor using the maximum mixedness model. Okay, this is how we have found. Okay, and earlier I have shown the integration methods. Okay, this let us find out the E of t and f of t data. Okay, these are the integration formulas we can use to find out the E of t and f of t data. Here we have given 5 points, 6-point formula. Okay, instead, because I have given small mistake, I have used this equation instead of this equation. You can correct, but there is no greater difference you can expect. Okay, let us find out the E of t first. Given the time information and concentration information, you have to find out E of t information through this equation, C of t by integral 0 to infinite C of t dt. So once you get this integration value, you can simply use this particular equation to find out the E of t at different times. Once you know the E of t at different times, you need to find out the f of t at different times. How to find out f of t information? F of t is nothing but integral 0 to t E of t dt. Okay, that means integration, that means you have to find out f of t at different times, time t equal to 0, t equal to 1, t equal to 2, t equal to 3. So to find out the f of t information at time t equal to 1, you have to add up these two, because cumulative means adding up. this particular value, example, the time t equal to what is the f of t value at time t equal to 2? Cumulative of these two numbers. What is the f of t value at time t equal to 3? Integration cumulative of 3 numbers. How to find out the cumulative? Simply you need to find out the values first. So to find out at time t equal to 0, what is the f of t value? It is 0. What is the f of t at time t equal to 1? Cumulative of these two, in the sense you have to apply the integration for the first 2 points. If you apply the integration for the first 2 points, you get f of t value. What is the f of t value of time t equal to 2? Integration of all the 3 points. So how to get the integration of all the 3 points? You have the different integration formulas. You can apply that for the 2-point formula, 3-point formula, 4-point formula, 5-point formula, 6-point formula. Like that you have to apply the integrations. You are going to get f of t values at different times. Okay, this is the time information. T information, C of t information is given. We have found out E of t information, f of t information, 1 minus f of t information. If you know the f of t, you can calculate 1 minus f of t. Then E of t by 1 minus f of t. You can able to find out that particular information as well, because why need to find in the f of x function we need information of k, E of t by 1 minus f of t. That is why we have found out the specific column, that E of t by 1 minus f of t. I have all the values got to find out the conversion. So simply at time t equal to 5, you can see simply you have to plug in the all the values. So to find out the conversions. So what is the actual conversion you are supposed to find out? What is the conversion at time t equal to 0 or lambda equal to 0? Simply you get the final conversion from this particular final equations. So you are going to get at time t equal to 0, that means at the entrance exit of the reactor, the conversion is 18%. This is how we can able to find out, given the tracer curve data, how to find the conversion from a reactor. This is assuming the maximum mixedness model. So there is one more simple example. Earlier, based on the data, okay, let us find out if the E of t and f of t functions directly given, how to evaluate. Okay, because based on the tracer curve data, you have found out what is the E of t values and f of t values. But in this example, data is not given. Instead of data, equation is supplied. If equation is supplied, how to execute, how to find out the conversion. Estimate the conversion from a non-ideal reactor using maximum mixedness model. So given the non-ideal reactor, the first order reaction, the K information is given, volume of the non-ideal reactor, volumetric flow rate, and E of t. That means through the tracer curve experiments, they have found out that E of t data is 1 by tau into e power minus t by tau. And you can able to find out, if you know the E of t, you can find out the f of t. F of t nothing but 0 to t E of t dt. So if you follow this integration principle, you get f of t equal to 1 minus e power minus t by tau. So I know what is an 1 minus f of t is nothing but e power minus t by tau. So I have the values of function of E of t. I have the function of 1 minus f of t. Simply you plug in this particular conversion estimation from the maximum mixedness model. If you substitute the respective expressions, then you can able to find out dx by dt is equal to x into k plus 1 by tau minus k. Okay. Simply this is a constant, k plus 1 by 2, keep it as a constant, and simply if you able to evaluate this integral, you can find out the conversion. Okay, simply you bring the a plus kt at the denominator. So you have to integrate up to the limits. At time t equal to 0, the conversion, that means at one end of the reactor, the conversion is x, that means time t equal to 0 here and time t equal to t here. Okay, at time t equal to 0, the conversion is maximum here. That means all the molecules travel to the end of the reactor by this time. So most of the molecules got reacted. So therefore at time t equal to 0, conversion is x. At time t equal to t, life expectancy, because molecules have just entered, so the conversion is 0 here. So you have to apply the integrations between these two limits, and you are going to find out at time t equal to 0, conversion is maximum conversion. At time t equal to t, the conversion is 0. So if you evaluate this particular integral, finally you get the conversion as k minus k by e power at by a. Okay. That means we know the values of k, we know the values of a, we know the value of t. What is the t? What is the time you are supposed to take? Okay, how much time you are supposed to take? Time. From the tracer curve data, the maximum amount of time spent by the tracer molecules in the reactor is 5. Okay, that means the time you have to supply in this time t equal to t, you have to evaluate the integral time up to t equal to 5 minutes. So finally